Hi everyone, my name is LayWai. I am a performance engineer from a data center group of Intel. My background is actually material science, where I work a lot on nanotechnology related work. I always love numbers and mathematics, and so I apply math modeling to help me to solve the complex problem. So I'm also a certified Six Sigma Master Black Belt. So I care a lot about effectiveness, efficiencies when it comes to work on a problem and a process. So today I'm going to introduce you an effective and efficient optimization method by using design of experiment. I'm going to show you that through a case study with a Ceph storage. This is the objective for my talk. I will cover the design of experiment, in short, DOE. So I'm going to use the 5 Ws, and then I'm going to show the differences between the one factor at a time, or you can call it OFAT. Then we're going to cover the methodology just lightly for the DOE. Then we will look into the case studies, where I'm going to use two different types of storage clusters. One is with OHDD and the other one with all SATA SSD. I will show you the DOE tuning results, how effective it is and efficient it is. So before I continue design of experiments, I want you to think about the scenario I show in the slides. Does it happen to you? Have you ever tasked to solve a complex problem with many variables? Another example, have you ever thought about interactions between factors? So what is DOE? DOE is a systematic approach to a complex problem solving. So it applies principles, techniques at the data collection stage, and so that it ensures the generation of conclusion that is valid, defensible, and supportable. Have you ever thought about that? It's valid, defensible, and supportable to the data you have. Who should use it? I think it should be used by engineers, researchers, and developers, but now almost all the scientists, engineers, and researchers, they're still using OFAT, one factor at a time. I'm going to show you the differences later. And why DOE is simply much more effective and efficient than OFAT. OFAT is change one factor and then make the other constants. So it also based on intuitive, so that it's more like a style instead of a planned experiment. So I'm going to show you a scenario, the result by OFAT. This is a real case, but the information is already changed. It happened before when I was an engineer in a production line. We're trying to improve the yield from a process. So the engineer I work with, he has many years of experience. About 10 years experience on the same process. When the new generation coming, we keep changing materials, right? When you change the material, you're going to change the process parameters. So what he did is, as you can see, he has 7 trials here. So he constants the pressures at 125 psi, and he changed the temperature. So when the trial ones, pressure at 125, temperature at 30 Celsius, he run the test with this setting and measure the yields, and so on with here. So basically what he's doing is a one factor at a time. So when he hit the temperature at 34, he find out that the yield is actually dropping to 86 instead of a higher than the 92. So he say, yeah, 33 is the best for temperature. Then he constant the 33 and then continue to change the pressure, that variables. So he reported out that is the optimizations, 92% of yields. 92% of yield in a production line is very low. So always we trying to hit into the area that is like 95. So we use the approach of DOE. And then we have what you see there is actually the yield contours of the real situations. So I also show you that the one factor at a time, the trials show by the black color dots, that is a one factor at a time where he find out that is at 92 area. So with the DOE, we actually able to hit to the 95. Factor, why DOE? Because the factor interaction. The previous case, he cannot find out more than 92 yield percent. That's because the one factor at a time cannot estimate factor to factor interactions. I'm going to show you a very simple case everybody know, and then you can understand what is factor to factor interactions. Think about open door. Open a door, okay? You are an engineer and your task to find out how to open a door. And the door, this product has a handle, okay? So you have two factors. You turn, this is one factor, or not turning it. And the second factor is pull or push, right? So one factor at a time, you constant the push and pull, now you do the turn. You turn or not turning, the door will not open. Now you constant the turn, you do the push and pull, the door is still not open. Are you going to conclude your finding is the door will never have open? No, right? In the DOE, we calculate out the main effect and also factor to factor interactions. Can you imagine each of the variables you're testing, you're able to calculate how much impact it is to the output that you're interested on. You're able to calculate them and rank them, and then you're able to calculate which factors is interact with each others and has impact to your output. So this is a two factors interaction. That is a three factors interaction, four factors interactions. In physics, usually we say that is so the impact is so low that we can just annoy it. The three factors interaction in our life. Can you think about a case? I can tell you, like when you increase the security, the safetiness, like medication bottle cap, you want to avoid the children to open it. So you design it to require three factors interaction in order to open it. For an example, you need to squeeze it, turn it, leave it. Missing any of it, it will not working. So that is a three factors interactions. So for you guys who working in this area, you are dealing with a lot of coding, a lot of parameters in your storage software. There must be a lot of interaction. So when to use this method, when you do comparative, screening characterizations. Screening means that, let's say you have 10 variables to test on. You want to screen out like which factors has the most impact to your output that you care about, that in the future, you know how to tune the values to meet your goal. And then it allows modeling and optimizations. Where you can get it, you can get it from R, Actions, and some other commercial statistical package like SAS, Jump. That is what I use most of the time, and the rest. So the recommendation flow, this is what I have been used. It's a high level. I always start with the problem statement. Let's say an engineer, performance engineer approached me, asked me how to tune a cluster with Ceph. So I'm going to ask detail like what is the problem behind, define the boundaries, and get out the objectives, everything. Because this stage is very important. And as a master black belt, I mentor a lot of projects, and I find out that no matter how many years you work in your area, You always need to improve. And I find out that a lot of experienced engineers, they have a problem even on the first stage. You want to define well, so you don't boiling the whole oceans. Then we can get into the design of experiment. There is a full factorial and fractional factorials. I'm not going to cover the center composite here because the study today is the finding there is nothing about response surface modeling. So after that, you have the option to add center point, replicate, block, and resolution. I know you don't understand what does it mean, but it will help us in making a more valid output. Then you collect your data. After that, you do the data analysis. The tool, I use a lot of math, right? I believe in our daily life, everything we do is related to math. It's just we don't realize it. So I use a lot of statistical tool to help me to quantify my finding. Is that true or false? And I use 95 confidence level on my studies. So those are the tools I use to analyze my finding, all that. And then after I get out a valid conclusions, then we can obtain a mathematical model. So DOE, full factorial, fractional factorial. The general notations for full factorials is just simple 2 power to the k. So the k is the total number of variables you're going to investigate. Let's say you're tasked to investigate, let's say tuning the Ceph cluster performance. So there is 10 variables you're going to test. So 2 power to the 10. There will be a lot of tests, huh? That is a full factorial. The 2 is the level of the variable's value. So in DOE, we don't test. Let's say you're testing QDEF. Always you see people, when they do their experiment, they test the QDEF is like 1, 2, 4, 8, 16, 24, right? We don't do that in DOE. We only take 2 values of each of the variables. That 2 values is the minimum values and the maximum values of the range for the values of the variables you're interested on. Okay? So move on. I give you an examples. Let's say you have this is an example with 3 factors, 2 level. What does it mean? So start from very left-hand sides. You will see there's 3 factors, A, B, C, D, ABC, and each of the factors has 2 levels. So minimum and maximum. That is the range we're going to study. That is the boundary in the studies. So we coded it minimum as -1 and maximum as +1. So if you look at on the right-hand side of the table, that is the combinations of run. 2 power to the 3 is 8 runs. That is a full factorial. We're going to test all main effect, 2 factor to factors interaction and 3 factors to factors interactions. So on the trials ones, we have the factor A as minimum value, B as well, and C. So, and then you do the measurement out. So how they measure, as I mentioned, you can calculate the main effect, right? You can calculate out. So how we calculate out is just basically taking the average of the output. So that is the main effect plot at the bottom here. So let's concentrate on the factor A. Minimum -1 and the +1. That is the range you're interested on. When A is at -1, low value, the calculation on the calculation of the point there is actually the average of all the blue color, which pointed to the A is at -1. Then when the A is a +1 and you take the average, that's how we estimate the main effect. So if you don't have, if this effect, factor A, has no impact to your output, it will be a horizontal line. right? No matter it's a low value or high value, it's just flat out. So in this case, 3 factors here, they all has the impact to your response output. So this is the interactions, effect, plot, and calculations. So the interaction plot, as you can see here, you will see there's a 2 line. So we are in this case, we're trying to calculate out the interactions between factor C and factor A. So look at the example of the green color line. When A is at low value, how does C changing the range? How does it impacting this combination, impacting the output? So I believe you will get this slide, and if you're interested, you can look into it. So fractional factorial is what I use on the case study of the Ceph storage. So just now I mentioned if you have 10 factors, you're going to do 2 power to the 10 runs, which is not effective and efficient at all, right? So I use a fractional factorial. Anything that is more than 3 factors, 3 variables or 3 factors, I will use fractional factorial. When it comes to fractional factorial, we have resolution to guide us. So in this case, I always stay with the resolution 5, where I will cover all the calculate all individual mean effects, how does they impacting the output, and also 2 factors interactions. So now let's look at the case studies with the Ceph. I think this is what you are all interested on. So the objective, my hypothesis, as I say, this is not my background. So I'm trying to show that the DOE can effectively help the engineer to do tuning. So my hypothesis is DOE can screening Ceph configuration parameter and suggest a valid optimization setting. So therefore, I'm going to do the performance tuning by the DOE. The main part will be do screening factors and then improve the performance. So to do that and prove my hypothesis, I need to have experiment and validations. So I have 2 clusters, or SSD and then the HDD. You can consider that as a storage environment, 2 different storage environments. And my goal is to prove that the tune setting, the tune performance suggested by the DOE is significantly different and higher than the default setting. So this is the configurations of the 2 different storage I use, the HDD and then the SSD. There are many items, they are similar. 4 clients nodes and 5 cluster nodes for each of these different type of storage device. We are using 3 replicas as the policy, and that is 3 monitors, Ceph monitors. The Ceph mons is located on the first 3 cluster nodes. So this is the factors or variables I tested. All this is the Ceph parameters. I talked to the engineers who work on the Ceph a lot. So he provided me the list of the variables that I should go do investigations. So and I also coded them as A and B. So to simple give an explanation later. So my DOE plan, fractional factorial. The total runs is 266 runs, means how many tests you run. So 266, I'm using fractional, so it's a 2 power to the 11 minus 4. So that's why you see there's a 2 power to the 7. And I put center point. The center point will tell me if this mean effect is a linear relations to the output, or is an exponential or quadratic. So I also replicate it. That's why totally is 266. If I don't do replications, it will be 133 runs only. So each of the HDD, SSD, I'm using, I run 266 on each of them. If you are running the full factorial, there will be 2,048 runs, totally about 22 days. I'm using resolution 5. So calculate like each test I run 15 minutes. So totally I'm used 3 days to finish all the 266 tests for each clusters. I use about 1 to 2 days to do analysis and get more data to show you later, to do the comparisons. That is the workload I use for each of a different type of a cluster. I only use one workload to run all the 266. In the 266 run, those 11 variables, they will change their values and run the test. And the block size for the HDD is 256K, and for the SSD is 32K. All is using 100 random write. There is no random read on my DOE plan, all that. And I'm going to use the finding based on this one workload and apply across different block size to show you there's an improvement in different block size, and as well as different mixed workload, random read-write later. So this, I summarize the finding after analyze. The top is the HDD, and the bottom is the SSD analysis finding. So what you see that like on the HDD, there's only 3 effects that's impacting the performance. All the performance I analyze is using IOPS. So it suggested that the factor variables A6 and A4, each of them has a main effect. And A4 and A6, they are interact with each other. If you don't tune them well enough, you will not get the optimizations. So the level of the level of directions. So A6, you have to go as high as you can. And the A4, you have to go as low as you can. So that you get the combination there. The optimized value I find out on the typical my cluster, the cluster I work on, is showing there. And then I also compare with the default setting there. Bottom there, we find out that the SSD has much more two factors interactions that contribute into the output, the performance. It has 2 main effects, is dominated. So if you see the order of the factors effect there, those are the rank. Number 1, the factor number 1 has the highest impact to the SSD performance. So later you can open the slide and look at what is B3. And notice that 3 to 7, those effects, they don't have main effects to the SSD, but they are interact with each other. I mentioned before, if you use one factor at a time method, you can never test out any factors or variables interact with another factors. You can never. You can only know 1, 2, 1, 2. That is the things you're finding out. So 3 to 7, you can never see through your OFAT method. So please don't use OFAT again. So that's the finding I have again, and the values there, suggested value. So if you are using the similar configurations cluster I showed before and follow the setting, you should able to get the performance increment. I'm using a 95 confidence level to do my test. That means I allow 5% on the error. I did not show you the confidence interval here for each of the finding here. It's about 5 to 7%. So if you measure something, you set up the optimum value, right? You run your test. You should able to get the mean value in between 5 to 7 differences, plus minus. So this is the results. This is the results I found. What you see here is the IOPS and latency when changing the block size. Again, I want to mention, I only use 100% random write workload and then go through the test in the DOE. I did not test random read. I did not test other block size. I stay with 256K for HDD and 32K for the SSD. So I get out the combinations, the finding previously here. I follow the DOE setting, and I run the test by changing the block size, and I measure what's the output, and the same thing on the default setting. And I calculate out the percentage differences on the performance. This is the equation. So it's so clear, right? Everything is above positive, there's no negative. So the red color is for the IOPS calculation and the blue color is the latency calculations. So the HDD, we see that we can achieve as high as about 35% improvement, and the SSD is about 25%. So great, using one workload to run the DOE, it actually applied across all different type of the block size. Now how about different mixed read write? So I did that. I did different mixed read write. I also want to show that, I also want to find out that whether this random mixed read write improvement happen on small block size and large block size. Does it apply on both? For most of the case, yes, it did, right? But for the HDD, I find out once you're above 90% of a random read, you don't take the benefit from the tuning. Instead, you are lower than the default. So this is I conclude it now as a sensitivity of the storage device using. So if I want to tune a HDD storage, and I will need to get information like what kind of workload your business care the most, or the range, then I will tackle that range and run the DOE. So I think this is the last slide. And then at the end, this is the last slide to show the latency. So I'm going to end my presentations with my summary. I introduce you an efficient method. You probably don't understand the DOE in this 30 plus minutes, but it's really benefit you. At Intel, we use a lot in our process line. So I kind of challenge myself to move to a data center group and trying to apply this method into this area. So this method I show you is a systematical problem solving approach. And I also show you in 7 to 8 days with one type of workload, you're able to improve 35% or 25% on two different types of the cluster. So it effectively do the screening, characterizations of your variables, all that. It can provide you the mathematical model for tuning purpose. I also show you that it effectively improve on both type of a test environment. And one type of the workload show the improvement on different block size and different mixed read write. And at the end, this type of tuning, it does not violate your policy. So I say thank you for your time and your patience on a new topic to you. Do you have any questions? Thank you. Yeah, sure.
Is any of this methodology available in the outside world?
Oh yeah, this methodology, before I born, is already there. Before you born.
Where should we look? Any pointers?
Any online, just search design of experiment. It will pop up. Yeah, you can use Excel to do it, but the Excel is going to make a lot of human error. Yes.
So on a couple of slides, specifically slide 33, you showed that SSDs had much more number of interactions between two factors or two parameters. Is this something that your experiment reviewed to you, or is this something that was told to you by engineers?
The engineer, so I want to use this because I have seen a senior engineer that working on tuning a while ago. He spent about half year and then he find out on HDD, he find out few of the finding, it's about half years. And the optimization he found is about 10 to 15%. And I look at the work and I find that this method can be approached. So I started to question them and say, I'm going to do this. Please provide me information. So he actually provided me the list of the variables that I can test on. And he don't know which one will have an impact and which one not.
Right. So what I'm getting at is, so once you have this list of factors on the next 23 slide or whatever, the next couple of slides later, you show that, for SSDs, the number of interactions between these factors is higher. What I'm asking is, did you find this with the experiment, or is this something also that was provided to you by the engineer?
I found this with the experiment. The DOE actually go through the analysis I have, that I show you a flow chart just now, there's a white color box. Those analysis actually pointed at the end conclude that this is the impact that will improve and do something to your output that you're interested on your response. So we don't know anything about any factors and interactions.
Right, got it. So, and the last question I had was about the read-write mix ratio that you showed at the end. So why was the read-write mix ratio not a part of the factors here? So why did you have to modify it after having identified the A and B factors?
Remember, I only use one workload for all my DOE tests, right? And usually, people will question me and say, since you're using one workload to run all the tests, so the improvement is only valid for this one workload, right? Any new workload will require new tests again, right? Because I'm trying to suggest to them it's not efficient way to have like one QDEF, two QDEF, 4, and then do a range of it. It's not a way to do it. So I'm trying to provide these ideas. That's why I'm stay with one workload. I want to find out that, I want to prove that one workload, you're able to get out the tuning effect, the results, by applying those tuning setting, it actually also increasing other workload. So you just run this one test and it apply across. Any more question? Challenge me. I love challenge from like people like you. No? Is it too easy to understand? So I hope this will be helpful to you, and if you are interested to use this method approach on doing something on your work or that, you can always contact me. I can provide you the design, how to run the setting combination, all that. But it depends on how much confidential level you can share with me. It is. When I ask about customer the policy, they are like, oh no. So I also do using the same method on the failure mode, where also on the Ceph cluster, because that's what I have. So what I did is actually find out which recovery parameters can reduce the mean time to recovery, and also like changing the performance loss, all that. Okay, thank you.